Okay, we started section 3.3 last time, and we talked about definitionally what it means for a function to be increasing and decreasing. And then we talked about the first derivative test, which allows us to make decisions about where our functions have maximums or minimums based on first derivatives. And these were our descriptions and images for increasing, decreasing, which were not anything new, but the first derivative test probably was a little bit. So if we have a derivative that's positive, it means that the original graph was increasing. If a derivative is negative, the original graph was decreasing. And if the derivative is zero, it's constant. And it also might, this is all over an interval. So what we had seen happen in earlier sections is if the derivative is equal to zero, it potentially has a change of like changing from increasing to decreasing. But this is over an interval, so it talked about it being constant. And taking a look at the first derivative test as a result of that, we talked about having maximums and minimums when it changed directions. So when it changed from positive to negative on the derivative graph, it changed from being increasing to decreasing, and it had a maximum. Likewise for a minimum, and if the same sign happened, then it ended up not having a change in direction. And so I gave an example of y equal x cubed. We did this example last time where we looked for functions to be increasing and the function to be increasing, decreasing. And while it didn't specifically ask for it, we actually talked about where we would have maximums and minimums from this first derivative test perspective as well. All right, so we're going to take a look at a few more examples along those lines today. The next one's going to involve a trig function, cosine. And remember, anytime we're asked to find about increasing and decreasing, we're asked to find the derivative. So we need the derivative first of cosine squared. So what do we have to do when we're doing the derivative of cosine squared? Somebody said chain rule. We do. We have a power of 2 and we have a cosine function itself. So the power of 2 will come down. I will rewrite the cosine function. It's now to the power of 1, so if you want to write the 1 right now, you can. And then the derivative of cosine is negative sine. Okay? Then we have the derivative of negative cosine. So what's the derivative of the negative cosine of x? What do you have? Yeah, it'd be positive sine x, yes. Sorry, I was checking for the sign itself. Yep. All right, look good? Okay. So what we're trying to do is we're trying to find out where that is equal to 0 so that we can create that sign chart. Remember the sign chart looked like this over here. So we're looking at the intervals in between the zeros. So we need to know where the zeros are to create the sign chart. So we set this equal to 0. When we work with, well, let's just look at this one last time so that we have a reference point. When we're working with something that has a fraction, we actually combined it to a single fraction, and we looked at the numerator equal to 0 and the denominator equal to 0, right? Okay, so on this one, there's no numerator and denominator, but I still have to somehow do some sort of factoring to make it work. So it does not make sense to simply move like the sine of x to the other side and then start doing dividing. Whenever you divide with variables involved, you lose potential places where it's equal to 0. So we don't want to do that. We always want to keep everything situated on the same side as long as there's any polynomials or trig functions involved to solve for. So we're going to simplify the first piece. So it's negative 2. I'll write sine first, but it doesn't matter. Sine x, cosine x, and then plus the sine of x. That doesn't actually help me in terms of solving. It just cleans it up a little bit. And what I'm wanting to do then is I'm wanting to factor it. So just like if I had a polynomial, I'd be trying to factor out anything they have in common. These two pieces have a sine x in common, right? So we're going to factor the sine x out of this. So sine x, and then I have negative 2 cosine x, and then it's plus 1. Okay, is that all right? Okay, so again, just like with polynomials, once we get it into factored form, we're going to set each piece individually equal to 0 to solve. So this is unit circle kind of stuff. We've got sine x equal to 0, and then I've got negative 2 cosine of x plus 1 equal to 0. Okay, the first one is the easier of the two. Oh, and I didn't make mention of it, but let me highlight it at the moment now. We're actually looking on just one rotation of the unit circle. So I did the wrong direction in the air there, like this, right, from 0 to 2 pi all the way around. So we want to make sure that we're only considering those values. So on the unit circle, sine values are the y values. So within the unit circle, the two locations for the sign value to equal 0 would be at this place and at this place, because my y values don't actually have any value there, or there's 0 there. So my angle measures are going to be at 0 and at pi. You could leave the 0 off. It's not really necessary because it strictly said between 0 and 2 pi, so the 0 is not going to be a possibility. It's sort of an endpoint. It caps it. So pi is our only new information piece from that. The other one we would solve, so I'm going to shift the negative 1, or the 1 over. So negative 2 cosine x equals negative 1, and then we'll divide by the negative 2, so the cosine of x is equal to 1/2. All right, so cosine of x equal to 1/2. Does anybody remember where that would be? Let's talk quadrants first. Where would cosine of x equal to 1/2? What quadrants would it be in? Okay, I'm going to do the easy one, 1, because it's positive, right? Cosine and sine are both positive in quadrant 1. Where else is cosine positive? In 4. Yeah, so it's these two quadrants, okay? So in quadrant 1, I need a x value, because cosine is my x value of 1/2. So that would be this point right here. I'm at this angle. Do you remember what that angle is? It's pi over 3. And I would have an equal value down here, too. And I need to figure out what that angle would be. So what would the angle be? And it goes all the way around. I mean, it's negative pi over 3, but I need to go this direction because I'm supposed to be between 0 and 2 pi. So what would I have? It's 5 pi over 3. And if you weren't sure, another way to get that, sort of from some arithmetic we could do, is this is negative pi over 3 because I'm going the opposite direction. And if you just add 2 pi to that, so negative pi over 3 and then add 2 pi, you'll get the 5 pi over 3. So if you're not sure, you don't remember that piece, it's another way to think about it. So it's at 5 pi over 3. So these two x values is at pi over 3 and 5 pi over 3. So I have 3 values to put on a number line. 1, 2, and 3. Pretty good with that? Okay, so generally speaking, when I'm working with trig values, they're going to cap it, like between 0 and 2 pi, or maybe even between 0 and pi or something like that. So you're not doing the whole number line because sine and cosine are cyclic, and they keep doing this repeating pattern of things generally. So we're looking at a defined interval. So it starts in this case at 0, and it ends at 2 pi. So when we write our intervals for increasing and decreasing later, we need to remember we're capping the ends of that. And then I need to put these on here in order. So which one comes first of the 3? Pi over 3. And again, we're not trying to get like the measurements to be perfect or anything. We're just trying to put them on here to give us some intervals. What's second? Pi, leaving my 5 pi over 3 last. Okay, so we need to choose values in between these. You're welcome to choose pi values, right? So like if you're like pi over 3, oh, well, I could just do pi over 4. Great, that's fine. You can also choose integer values because we don't care what the number values are. All we care about are the signs. So to be perfectly honest, integer or even maybe fractions like a 1/2 or something are a bit easier to work with when I'm plugging them into my calculator. So that's what I tend to do. So if I need a value that is smaller than pi thirds but bigger than 0, what could I use? Pi over 4 would, but I was thinking in terms of like without pi's. That's what I was referencing. How about 1? Could I use 1? How do I know 1 is smaller than pi over 3? Because pi is 3.14. It's slightly bigger than 1, right? Or slightly bigger than 3, and then dividing it by 3 would make it slightly bigger than 1. So 1 would work. Pi over 4 would work just fine too, Allie. There's nothing wrong with pi over 4. I'm just going to put them in my calculator anyway, so if I can keep my keystrokes to have to not have anything else extra, then I'm going to try to do that. So we're going to put in, let me change my mode, we're going to put in the derivative function, And you can do it in this factored form if you wish. Any of these forms you can put it in. It doesn't make any difference. Just pick which one you want to put it in and put it in that. Do make sure, we've done this before, but do make sure, especially if you've used the calculator for other purposes, that you have your function or your mode in radians, not in degrees. Okay, so mine's in. So I'm going to choose the number 1. So this is about 1. It's a little bit bigger. And pi is about 3.14. So what could I choose in between them? 2 would be fine, or even 3 would be fine, right? So I'm going to choose 2. Mention 2. So this is a little bit bigger than 3. 5 pi over 3. Grab your calculator, put 5 pi over 3, and what is it about? Do you have it, Cole? What is it? It's about 5. So would 4 between them work? Okay, cool. We'll use a 4. And then after the 5 pi over 3, so this is about 5. This is a little bit bigger than 6, right? So you can choose 6 would work here. Again, if you want to use pi half kind of values, that's totally fine. It's not going to hurt anything. But I tend to use integer values when I'm going to use my calculator to plug them in, and all I care about is the sign that's happening anyway. So when I put these in, when I put in the number 1, I get a negative. When I put in the number 2, I get a positive. The number 4 gives me a negative, and the number 6 gives me a positive. Did anybody not give them those signs? Okay, these happen to be oscillating. That happens a lot with trig functions, but it wouldn't have to, right? It wouldn't have to. There would be potential for places where we could have it go negative, negative, or positive, positive. So just be aware of that. All right, so we're looking for where it's increasing and decreasing according to the directions. So the negatives tell me it's going to be doing what? Decreasing. So it's decreasing from 0 to pi thirds. And you can put a comma. I don't care what you do when you write it. The WebAssign may make you put a U for union. And then it picks up at pi to 5 pi thirds. Those are the decreasing. Let me shift this up just a little bit. And then it's increasing on the positive pieces. So those are the in-betweens that I skipped, right, in the outside one. So this is the pi thirds to pi. And then the 5 pi thirds to 2 pi. Could we look at relative maxes and mins here? Sure we could, right? First derivative test says that if it's going, use my other pen, it's going down and then up, there's going to be a local minimum here. And if it's going up and then down, I've got a local maximum here, and I've got another local minimum here. This question didn't ask me for that, but I certainly could be grouped with this question and answered in the same, with the same work anyway. Any questions on that? Okay. We're going to change directions slightly for the next couple. This one is asking us to do much of the same thing. It's just identifying the pieces in a little bit different structure. So it says find the critical numbers, if any. That's what we were doing before, setting it equal to 0, or doing the derivative, setting the derivative equal to 0 or equal to does not exist. Finding the open intervals where it's increasing, decreasing. That's actually exactly what we did on the previous problems. That's where we stopped. And then C is the finding the maxes and the mins, right? The relative maxes and mins that I was sort of pointing out that we could have done on the previous ones if we had been asked. And then the last thing says to graph the actual original equation to confirm your results. That is to make sure that it is what you're expecting. I do really have a maximum at about that value. I do have a minimum at about that value, at least in as much as your calculator can be precise. Okay? So we're going to take a look at a polynomial. Polynomials are very nice. In particular, this one, you know what it looks like. What is this a graph of? Parabola, like 3 of you are whispering underneath your breath and everybody else is thinking it and not saying it. It's parabola, right? Opening how? Downward, right? This is the image you should have in your head, roughly speaking. which means you know several things. You know it's increasing at the beginning. You know it's decreasing at the end. And whatever the vertex is the maximum point. You know all that. You know it from algebra, right? So we're starting with something that you're very familiar with from a completely different perspective. And we're going to show that the calculus works out exactly the same way. Okay? So the calculus is not hard on this one because the derivative is not hard. What is the derivative of this function? Negative 4x plus 4. All good, right? I told you there's going to be some really nice derivatives showing up in this particular chapter. And to find critical points, this is sort of like part A of what I'm doing right now. To find the critical points, I set that equal to 0 and solve. Now, this is a case where I do shift things around, right? There's no factoring that needs to be done, per se, in terms of with variables. So I am strictly going to solve this. This is negative 4x equals negative 4. What's x? X is 1. That's my critical point. So part B is creating the number line, and I only have one number on my number line. It's not a very exciting number line or sign chart that I'm going to create from it. And I need to test values on either side. So what's a value I might test before 1? Good. And after 1? Those are great. And we're putting them into the derivative. Okay, so you probably don't need to put this in your calculator to evaluate this, but if you wanted to, you certainly could. We're going to put the 0 into the negative 4x plus 4. And are we going to need to get a positive or a negative? We're going to do positive. And if I put the number 2 in, negative 4 times 2 and then plus 4, do I get a positive or negative? Negative. You get a negative. So this tells me that it's increasing from negative infinity to 1, and it's decreasing from 1 to infinity. Now, does that match with what we imagined? Yeah, I mean, we didn't put it on a grid or anything, but the perspective that it's increasing and then decreasing is definitely what we expected to happen. So no new information really from what we have done before. And then the third thing is to recognize whether I have a maximum or a minimum, or if I even have them, right? So this is increasing and then it's decreasing. So what happens at this location? It's a max. And it's a relative max, right? So on this one, it's actually an absolute max as well. You saw that happen back in section 1, 3.1. But that's not what the first derivative test gives us information about. It tells us only about relative or local maxes and mins. So this is a relative or a local maximum. So it's a relative max. And I want to put at the location, and it's an x value of 1, but I don't have the y value yet. How can I find the y value that goes with the x value of 1? Plug it into the original function. So if you go back to your original function, and we're going to graph it here in a minute anyway, so I'm just going to go ahead and put it in my calculator. We have negative 2x squared plus 4x plus 3. And if you want to put it in your table, you can. We're putting in the number 1, and at the value of 1, I get what? 5. That's what I have, 5. Okay, so this is how we would find all the information. The last part, part C, says that we're going to graph it. That's why I went ahead and put it in my calculator instead of just doing it by hand. I'm just going to use a standard window, I think. We'll see if it works. It works fabulous. So the standard window is the 10 by 10 window. And your graph looks something like this. Does yours look something like that? I hope, yes. This is the 1, this is 5. If you were tracing along it, you would find that. And sure enough, it matches exactly all the pieces that we've said and what our intuition told us already from what we know about parabolas, right? If you wanted to confirm that maximum or min, there's several things you could do. You could trace in your calculator. That would get you pretty close. There's actually also a max function in your calculator. You may not be aware of it, but it's probably worth mentioning. So if you hit, let's see which one's underneath. Underneath the trace button, do you see above, well, above it, do you see above trace the word, says calc? Do you see the C-A-L-C above that? If you hit the second button and hit the trace button, that puts you into the calc, as in calculate, not calculus, but calculate menu. And you can see it says things like value, 0, minimum, maximum, intersect, dy dx, integral of f of x dx, all these pieces of things that we can find. If we're looking for the maximum, which is what we're suggesting on this one, you can select number 4. And it asks questions. It says left bound. And once you are to the left of your graph, of the maximum, like if you're over here somewhere, I'm meant to use red, you can press enter. And then it says right bound, so you arrow over to the right-hand side somewhere, and you press enter, so you're over here. It says guess, you just get close to the maximum location, which would be right here, and press enter. And it tells you what the maximum value is. And it will tell you level of accuracy step. My calculator does not say 1.5. Does anybody's actually say 1.5? What does it say? Did anybody try that?
999.
Yeah, that's what mine says too, Brock. It says 0.99999, whole bunch of nines as the x value, and then it says 5 for the y value. Because your calculator is using numerical techniques to try to approximate it as well. It is not using calculus. You are smarter than your calculator. All right? So when you interpret this and you look at this, you have to realize the calculator has an error, and I'm smarter than that. I know that that's supposed to say 1.5. I'm good to go. Okay? So, yeah, we've got all those pieces showing up exactly like we're expecting from the graph. All right, we're going to try a bit more of an interesting one. The reason I say interesting maybe is because this one we could have done with college algebra. You didn't need calculus to do any of that. All that stuff we did in algebra, okay? But you need something more than algebra to do this one, right? X to the 1/3 plus 1. Directions are the same, so we're going through all the same steps. The first thing we do is take the derivative. All right, so what's the derivative of x to the 1/3? One-third x to the negative 2/3, right? And then the derivative of the 1 is 0. Okay, so we're going to set this equal to 0 or does not exist. And the reason I specifically say does not exist here is because I recognize that I've got a negative exponent. And negative exponents are going to put things back into a denominator, and denominators aren't allowed to be 0. I didn't have to think about that over here. There's no denominators that were showing up, so setting it equal to does not exist does not make any sense. But over here is probably going to be necessary. So as we clean this up and you rewrite this, it will look like this. I'm going to just leave it as the 2/3. If you wanted to write it as the cube root of x squared, you could certainly do that. So I'll write it that way too, just to remind you. Either of those versions of this exist. And we're wanting this to equal 0, but in order for it to equal 0, the numerator would have to equal 0, and it just doesn't. It's 1. It's never going to equal 0. So I'm never going to get this to set equal to 0. But I very well could get this to set equal to does not exist, right? And where would this be not existing? Where would this derivative value not exist? At 0, right? And this happens at x equals 0. If x is 0, the denominator will give me 0, and then I will not have a function value coming out of the derivative. So this is part A. And then part B wants me to put that on a number line. So here's my number line. And I want values on either side. Now, back in the original function, we didn't make mention of it there like we did further on, but this is the cube root of x, right, plus 1. If it had been square root, the situation would be slightly different. If I have a square root of x, I can't have a negative underneath it, the radical, right? But with cube roots, you can, because things can multiply the other 3 times and give you negatives. So the domain for this function really is the entire number line. Okay, so breaking it apart at x equals 0 actually does make sense here. Whereas if I'd started out with the square root of x plus 1, it wouldn't even make any sense to talk about the negative values. They aren't in the domain. But they are here. So I need a value slightly before 0 and one, not slightly necessarily, but anywhere before 0 and anywhere after 0. So what's a number before 0? Negative 1. That's a good choice. And after, might as well use 1. Okay? And again, we're looking at what happens in the derivative function. So you're welcome to use the 1/3 x to the 2/3, but for me, it's easier to think about it with the radicals. Because take a look what happens when I put a negative 1 into this x squared component of the second version here. What's going to happen? It's going to be positive, right? Because it's going to get squared. So this negative is going to go away. It's going to be squared. It's going to be positive. And then I'm going to take a cube root of something positive, which is going to keep it positive. Then I'm going to multiply it by 3. That's not going to change the sign. And I'm going to do 1 divided. It's all going to be positive. So even though I have a negative 1 input into this, because of the square, the negative gets eliminated. And certainly when I put in the number 1, I also get them to be positive, right? So this one doesn't actually have any relative maxes or mins. That's what actually I know is going to happen on part C here. Part C here in a minute. But what it does tell me is that it does stop increasing briefly, and then it starts up again. So my increasing does not just say negative infinity to infinity. My increasing goes from negative infinity to 0, where it stops increasing for a moment, and then it picks up right afterwards and goes from 0 to infinity. We'll look at a graph of this in a minute, and you'll see why it's doing what it's doing. But this is correct. And as a result, although we've already mentioned it for part C, there are no relative extrema, or local extrema if you prefer. So take your calculator, and we're going to confirm what happens in the calculator with the graph, and we're going to talk about something that we have not seen happen yet at all. We briefly spoke about it once, but we haven't seen it happen yet until now. So take your calculator and put in the x to the 1/3 plus 1, or you can write it as cube root of x plus 1, your choice. I think a standard window will be fine. So the negative 10 to 10 or zoom 6, yeah, it will. Your graph looks something like this. I'll change colors to distinguish it. That's not great. Let's try again. It's not perfect, but it looks something like that. And it keeps going like this. Okay, does your graph look like that? Okay, so notice what's happening at 0, at x equals 0. At x equals 0, I'm right here. It's certainly increasing before that, and it's certainly still increasing after that, so that matches. There's certainly no relative max or min there. But what is happening there? Can you tell? A vertical slope, a vertical tangent line. We've talked about that, but we haven't seen it happen. There's only a few places where derivatives don't exist. They don't exist for sharp turns. They don't exist for discontinuities, right, jumps in the graph or asymptotes. And they don't exist for vertical tangent lines, and this is an example of a vertical tangent line. And it fails there, right? The derivative was equal to 0. The function still had a value, so that's interesting, right? We don't always have function values when derivatives fail, but this one we do. The derivative fails to exist because it's a derivative that has a slope that's an undefined slope. So if you were to draw a tangent line, it would be vertical, the slope would be undefined. Okay? So they're very uncommon. We don't see them happen very often, but I wanted to show an example of one that does. All right, last example. Some more trig going on. It says to consider the function on the interval, find the open intervals where it's increasing, decreasing, apply the first derivative test, and then graph. These directions are almost the same, and in fact, even though they aren't explicitly worded the same, they're the same. The piece that's missing is what? What's missing from the directions that were over here? Nope, increasing, decreasing is there. It doesn't say find the critical numbers, but you have to do it in order to find anything else. So even though it doesn't explicitly say find the critical numbers, that's inherent in the process. We still have to do it, okay? So don't try to, analyze these directions too much. They're all pretty much the same, even if they're not explicitly separated out the same way. So we are going to find the critical numbers first. We need to find the derivative. So what's the derivative of x plus 2 sine x? 1. 1 plus 2 cosine x, yes. Okay, everybody good with that? Okay, derivative straightforward. Set it equal to 0. So this is 2 cosine of x equals -1. Cosine of x is -1/2. We saw cosine of x equal to positive 1/2 earlier. So we've already discussed that a positive 1/2 puts me in quadrants 1 and 4. So a negative 1/2 will put me in quadrants 2 and 3. So we're here or we're here. And again, we're close to the y-axis, so we're at these values. What are those angle values? 2 pi over 3 or 2/3 pi. And, whoops, 4/3 pi or 4 pi over 3. Good. So over here, these x values, and I am still looking at it being, where was it? It's up here. It being on the interval from 0 to 2 pi. It just shows up in the directions instead of in the problem itself. So I am still going between 0 and 2 pi, so my unit circle that I drew made sense to do so. So I'm going from, or I've got the two values of 2 pi thirds and 4 pi thirds. So we're still working on part A because that's the critical points that it didn't specifically ask me for. But it did ask me to find where it's increasing and decreasing. So I need to do my sign chart. It is capped from 0 to 2 pi according to the directions. And the two values are 2 pi over 3 and 4 pi over 3. And we can pick numbers in those intervals just like we did before. So what is a number before 2 pi thirds? 1 would work, sure. How about between 2 pi thirds and 4 pi thirds? 3, right? Approximately pi, so approximately 3 will be a good, or pi or 3. And how about something between 4 pi thirds and 2 pi? 5 should work, and if you weren't sure, you could certainly use 6, right? We're just getting a little bit closer. All right, so take a look, and we're going to put this into the derivative. We're going to put the derivative, that's this piece, into y1. And I'm going to evaluate these three values, 1, 3, and 5. And I'm looking for the signs only. What sign did you get when you plugged in 1? It's positive. How about when you plug in 3? It is negative. And 5? We expect it to be positive. Did it work out? Yeah, it's positive again. Okay, did anybody's calculator not give them those signs? Okay, excellent. So, where's the graph increasing? Perfect. 0 to 2 pi over 3 and 4 pi over 3 to 2 pi. And then it would be decreasing between them. Hang on. I'm running out of space a little bit. So from 2 pi over 3 to 4 pi over 3. Is that all right? Okay, so that's part A. Then part B asks us to apply the first derivative test, so that's relative extrema. So I go back to my sign chart, and when it's positive, I just draw an uphill piece, right? Negative is down, and then positive is back up. So what happens right here? To max. We don't have the value yet, but there is a relative max at the x value of 2 pi over 3. We'll find the corresponding y value in a moment. And I need I have a relative min happening over here. Right? At 4 pi over 3. And I need the corresponding output value. These are not going to be pretty output values because I have a polynomial, namely x, combined with a trig function. These will not be nice. Okay? So we're going to evaluate them. I'm going to erase my unit circle for the moment since we're done using it now. But I'm going to evaluate these at the values 2 pi thirds and then we'll do 4 pi thirds. So at 2 pi over 3, I've got 2 pi over 3 plus 2 sine of 2 pi over 3. So what is the sine value? I erased my unit circle. But what is the sine value at 2 pi over 3? Cosine value is negative 1/2. What was sine? What was it? Square root of 3 over 2. Right. So this is 2 pi thirds plus 2, and it's square root of 3 over 2. That's off the unit circle at that location. The 2's can cancel, right? So I end up with 2 pi over 3 plus square root of 3. So it's not a very pretty value, as I warned you. The value at 4 pi thirds is very much similar. So if I do this at 4 pi over 3, I have the 4 pi over 3 plus 2 sine of 4 pi over 3. And it's not the same value, but it's similar. So what's the sine value at 4 pi over 3? Yeah, it's the same value, but it's negative because I'm below the x-axis. So my sine value is negative down there. So this is 4 pi over 3 plus 2, and it's times negative square root 3 over 2. So the 2's cancel again, but now I have a negative. So I have 4 pi over 3 minus square root 3 for the y value. Okay? We're going to confirm real quick with the calculator. Okay? So I'd like for you to take the calculator, change out what's in there now. We want the original function in there. And we're trying to confirm with the original function that at least visually it's reasonable for what's going on. So I have x plus 2 sine x. You might as well make your window really only go from 0 to 2 pi, because on this one it told us that, right? So x min 0, x max 2 pi. Your y min and your y max probably don't need to be all the way to negative 10 and 10. This graph, is only going between the x value of 0 and 2 pi, so that's to 6. Right, as a maximum, and the sine value itself is multiplied by 2. So maybe I'll leave it at negative 10 to 10, and I'll adjust it if I need to. That might not be a bad plan. Yeah, it's a little overkill, but it's not bad. So my graph ends up looking, I'll switch screens, like this. It's only on the top half of the quadrant, and it looks something like this. Yours looks something like that, give or take. Mine went from 0 to 2 pi here. So there is a relative maximum occurring, and we could trace to find out that it's at approximately 2 pi over 3. And there is a relative minimum occurring. Again, we could trace to show that it's approximately 4 pi over 3. The one negative to doing this is because I'm doing trig functions and I'm dealing with pi over something values, irrational numbers, your calculator, even if you find that maximum or minimum feature like I showed you how to do a little bit ago, it's not going to tell you that it's at 2 pi over 3, right? It's just going to give you a decimal approximation, and you're going to have to be okay with the fact that that's close enough because your calculator doesn't report things in terms of pi's. Yeah. Any questions on that? Okay, so WebAssign is due now for this, and we will come back again and meet on Wednesday.